And then we have an extra exercise called E1. And E1 is interesting because it gives us a very strange production function. So the production function is a function of x1 and x2, think of capital and labor, and it's a minimum, but unlike what we've seen before, at this functional form, we have the minimum of 2x1 plus x2 and x1 plus 2x2. So think of a firm or a plant where a certain product is produced, but in this plant we have two sectors, sector 1 and sector 2. They each use capital and labor, and things need to happen in both sectors in order for production to take place. So if sector 1 is supplied with capital and labor, but sector 2 of the same plant is not, then there will be not any output. And the ratio in which these two sectors use capital and labor is slightly different. And you are asked, well, at face value, a simple question: what is the cost function for this production technology? So, and when I talk of sectors, I also talk of techniques that are used in order to attain a certain production level, and I separate between technique 1 and 2 in what follows. So let's get started with this one. Again, taking derivatives and all that doesn't help you that much because we again have this minimum function. So what can we do? Well, we have a production function, and a first idea that you may have is why not draw some isoquants in order to get some feel for this particular production function. And that is what we will do. With isoquants, you have the production factors on the x and the y axis, in this case x1 and x2. And we will first consider the first technique, 2x1 and x2. So, and the question we ask in order to derive an isoquant is, how many units of capital and labor do we need in order to attain a given production level Q? And in our example, I will take Q equal to 4 units of output. Now, because x2 is on the y-axis, we first rewrite this first technique as x2 as a function of q and x1. And doing so, we note that the slope of the particular isoquant associated with this first technique is equal to -2. And we know that q then is the intercept, and as said, we will focus on a certain production level of 4 units of output. So the first technique is associated with an isoquant that have the following form, and this one is then for the particular output of 4 units. So if we would only depend on technique 1, we could produce 4 units of output by solely applying 4 units of input production factor x2, or maybe only 2 units of the production factor x1, or a combination of x1 and x2. That is the first technique. But then there also is the second technique, the second sector in our plant. And again, in order to arrive at isoquants in the picture, I rewrite this technique as x2 as a function of q and x1, which again gives us the slope and the intercept of the isoquants. And in picture, it gives you isoquants like this. And the slope is -1/2. The intercept with the y-axis, if you have the isoquant associated with an output of 4 units, is equal to 4/2, so equal to 2. So, and in this two-dimensional graph, every combination of x1 and x2 gives you a certain output level. But output in this plant is dependent on what happens in both sectors and the amount of production factors that you allocate to both sectors. So in order to produce 4 units, you need to satisfy this condition, and you also need to satisfy this condition over here. So both isoquants need to be satisfied, meaning that, for example, if you would use 3 units of x1 and 0 units of x2, your total production would not be 4, because plugging in 3 times 2 times 3 units of x1 gives you 6 plus 0. So having 3 units of capital and or of 3 units of labor and 0 units of capital here would give you in sector 1 an output of 6. But in sector 2, it would give you only an output of 3, because 3 times x1 is equal to 3. So you get 3 plus 2 times 0 is 3. And a minimum of 6 and 3 is 3. So if in the plant there would be only 3 units of labor and no units of capital, that would suffice for sector 1 to produce 6 units of output, but in sector 2 that would suffice only to produce 3 units of output. So in total, production could not be higher than 3. So to produce 4 units, both conditions need to be satisfied, meaning that the isoquant has the following form. In order to produce exactly 4 units, you need to use combinations that are on the yellow line over here. All these combinations allow you to produce exactly 4 units of output. So knowing that, we want to answer the question, how much capital and labor we should hire. So which specific point at this yellow isoquant we should need to be in order to minimize our cost. Yeah, so in the end, we want to attain the production of 4 units of output at a minimum cost. Now, what particular combination of x1 and x2 is used, of course, depends on the cost of x1 and x2. So our cost function is equal to the price of a unit of x1 plus the number of units of x1 we use plus w times x2. And again, we can rewrite this as x2 as a function of the total cost minus w1 over w2 times x1. And I rewrite it in this way in order also to be able to depict the cost functions, the iso cost functions, into this graph over here. So the iso cost function have a slope equal to minus w1 over w2. That's given over here. And the intercept with the y-axis is at the constant, at the given cost level of the iso cost function, capital C. Now then, there are 3 possible cases. It can happen that production factor x1 is very cheap compared to production factor production factor x2. So one possible case is that W1 is less than half of W2. In that case, it pays off for the firm to only use production factor x1 and its production. So it will be at the dot over here. So the way to see it graphically is that if this condition holds, if W1 is very small compared to W2, then the slope of the iso cost function is very flat. So it's negative, it's downward sloping, but it's very, very flat. So if you would depict it in the picture, you would have an iso cost function like this. This one is associated with a cost of C1. So the intercept with the y-axis is at C1. But of course, we can attain an output of 4 units at a lower cost. So we can lower this, and the lowest iso cost function that is tangent to our isoquant, the yellow one over here, is the one that touches on the isoquant in this corner, where indeed we only use production factor x1 in our production, and we have Q units of X1, that allows us to produce exactly an output of Q while we use no input, so no production factor X2. And you can see this because if you plug in Q for X1 in our production function and 0 for X2, then you have then the output is the minimum of 2 times Q plus of 2 times Q and Q. So the minimum of 2Q and Q, of course, is Q. So this allows you to produce exactly Q units of output. And we choose this particular combination because production factor X1 is cheap relatively to production factor 2. Then there's another possible case. So this is 1. And in this case, our total cost function, we don't use production factor X2. It's 0, so no cost for that. And our total cost is only determined by the number of units of X1 that we use, which is equal to Q, times the cost of this production factor, which is equal to W1. So this is our total cost function. Then the second case, the second extreme case, is where W1, production factor X1, is very expensive relatively to production factor 2. Means that the slope of the ISO cost functions are very steep. And in that case, we minimize our cost of production by using only production factor 2 in our production process. So in this case, X1 will be equal to 0 and X2 will be equal to Q. And that will also allow us to produce Q unit levels of output. So if we want to produce, say, 4 units of output, if X1 is relatively expensive to X2, then we will be at the point where we will use 4 units of X2 and 0 units of X1 in order to produce 4 units of output. That's the second possible case. In that case, our cost function is solely determined by the price of input factor X2, and we use Q units of that. And then we have a third case where, well, just our cost of X1 and X2 is somewhere in between. So none of the production factors is relatively very cheap or expensive compared to the other. In that case, we will minimize our cost by being at the kink over here. So in this case, the slope of the cost function is not very shallow. It's also not very steep. It's somewhere in between. And we minimize our cost function by taking the point where it touches upon the isoquant at the kink. So, and at this particular point, you will see that the production factors X2 and X1 are used equally, and we use Q over 3 of both. So for example, if we want to produce 4 units of output and the price levels are like this, then we will use 4/3 units of input of X1 and 4/3 of unit of production factor X2, as depicted in the graph over here. And if you would plug in Q over 3 for X1 and X2 in our production function, you would see that the minimum of the two would be exactly equal to Q, which is no surprise, because you have 2 times Q over 3 plus Q over 3, which makes Q, and this expression will also amount to Q. In this case, our cost function is equal to, well, we use both Q over 3 units of X1 and of X2. We multiply it with the cost of X1 and X2, which is W1 and W2. So the cost function is given by this expression. Then, of course, there are 2 borderline cases where the ratio between W1 and W2 is exactly equal to 1/2 or equal to 2. And then you're really at the threshold. Okay, so that solves for question A. Then question, so the cost function This is the cost function for the 3 separate cases. And you can write this very neatly in one functional form. So the cost function is the minimum of W1, W2, and the sum of W1 and W2 over 3. Because in the end, we want to minimize cost. And all these options allow us to produce an output of Q. So we just select the cost function which has the lowest value. Now, in all these cost functions have the term Q, so we can put that outside of the parentheses. In all cases, we want to produce Q units of output, but we select the cost function that does so at minimum cost. So we select that cost function always for which is minimal. So we take the minimum of W1, W2, and W1 plus W2 over 3. Then at B, what is the conditional demand function for factors 1 and 2? As a function of factor prices W1 and output Q. So, actually we already answered that in question A, but this is just summarizing the results. So we know that if W1 is low compared to W2, we will demand Q units of production factor X1. So that's the point over here. Then when W1 is very expensive compared to W2, we will not demand any units of input of production factor X1 at all. In the intermediate range, we will demand Q over 3. And then at these borderline cases where W1 is exactly equal to half W2, then it will be somewhere in between Q and Q over 3. But you can just allocate, it doesn't matter for your total cost. And also here, when W1 is exactly equal to 2 times W2, then our demand for production factor X1 will be in between 0 and Q over 3. But how you exactly allocate between X1 and X2 doesn't matter at that point. So once you have solved exercise A, you already have also solved exercise B. But to write the contingent demand, and you can see that this is contingent demand because the demand for production factor X1 here is written as a function of the prices of the different production factors and the quantity that we want to produce. And this completes the extra exercise.